Hello, this is Riki Rajmashinpali. This is my lab report on constant velocity for my Physics 2211 class at Georgia Tech. In the lab, I compared the motion of a ball in real time to a computational model of the ball's motion. The format I will be going over in the lab is by first giving an introduction, then going over the analysis of the ball's motion in real time using Tracker, then going over the computational model of the ball's motion using GlowScript, then comparing the two models based on their position versus time graphs, and lastly, going over some essential questions. The purpose of the lab experiments is to observe Newton's second law of motion, or the momentum principle, in a real-world setting, and then verifying its accuracy through comparing to experimental and computational models based on position versus time graphs. Newton's first law of motion states an object will remain at rest or in uniform motion, constant velocity, unless acted upon by external forces. Constant velocity occurs when the net force acting on the object equals zero, and it's shown in the formula. Position update formula can be shown as stated. The Newton's second law of motion is when an object is acted upon by a force, the time rate of change of its momentum equals the force, or force equals mass times acceleration, or force equals change in momentum divided by the change in time. From that, we can derive the velocity update formula as stated. The procedure of the lab is as follows. Record a video of rolling the ball in a straight line, import the video in Tracker, and analyze the obtained position time graph of the experiment. Edit the starter code in GlowScript based on the data from the Tracker software, and run to obtain data and position time graph of the computational model. And lastly, compare the two graphs. I took a video of me rolling the ball and uploaded it on Tracker to plot its position as a function of time. I rolled my ball from right to left, where the axis is negative on the left side and positive on the right side. This results in a downward sloping graph of position versus time as seen in the video. The initial position of the ball was 0.0001597 meters, and the velocity was negative 0.387 meters per second. Since this velocity is supposed to be constant, assuming there's no friction or air resistance, we can find the velocity by calculating the displacement between 2 points and then dividing by the time elapsed between those 2 points. I took the first two data points seen in the video where the times were 0 seconds and 0.033 seconds. The link below directs you to the full code used to create my computational model. For the initial values in line 38, I didn't edit the mass since I wasn't able to find a scale to accurately weigh it, but I also knew that mass does not matter when calculating the velocity. In line 35, I put the coordinates for the position of the ball at time equals 0 to represent the initial position of the ball. In line 38, the vector represents the initial constant velocity obtained by finding the displacement over time for the first 2 points of my Tracker data. In line 40, it did not need to be changed from the original 0.01. I made it 1/30 since my video had 30 frames to make the data cleaner to observe. I believe the time interval is still small enough to provide accurate results. For calculating the loop, in line 49, I made time less than the last time value recorded in my Tracker data, which was 1.002 seconds. In line 54, I changed the vector from 111 to the 0 vector. In line 58, I wrote the velocity update formula discussed in slide 4 in Python. In line 60, I wrote the position update formula discussed in slide 4 in Python. These are two graphs I obtained by running my computational model. Similar to the position versus time graph created in my Tracker video, this graph is also negatively sloping graph. Unlike my Tracker graph that looks linear but is not technically linear, my computational graph gives an actual linear slope as shown by the straight horizontal line in the velocity versus time graph of the computational model. Data collected from my two models, I put them in the Google Sheets to plot the two sets of data points on the same position versus time graph. As can be seen, the lines and therefore the models are very similar, although there seems to be a very slight deviation towards the end of the graph, with the computational model covering slightly more distance than the experimental model. This also means that the computational model shows the object moving slightly faster than the experimental model. One reason for the difference in the graphs is that I rolled the ball on a flat marble floor, but there still might be some slight friction and also air resistance that acts as external forces on the ball. This goes against the assumption that the net force is 0, hence the ball is slowed down in the experimental model compared to the computational model. The ball might not have been rolled perfectly in a straight line in view of the recording camera, and also, since I plotted the points on the Tracker by hand and by human eye, there is obvious human error. What if the axes were flipped when analyzing my video data in Tracker? In this case, the magnitude of both the velocity and position would stay the same. However, velocity is a vector, meaning it has direction. Therefore, the direction would change, and my ball, which was moving along a negative direction along the x-axis, would be moving in a positive direction along the x-axis, resulting in a positive linear slope of the time position graph instead. What does it mean? Is it possible for you to say how many pushes and pulls are added together to give zero net force in this case that you observed. Assuming the ball is moving at a constant velocity, the four forces acting on the ball are friction, applied force, gravity, and normal force. The normal force and gravity are equal in magnitude and in opposite directions, resulting in no motion on the y-axis. The applied force is zero since the acceleration is zero, as the velocity is constant, and we are assuming there is zero friction and air resistance, resulting in constant velocity in the x-axis. This is supported by Newton's first and second laws of motion.